Hello. So today we're gonna start by learning some literal equations, and we'll do probably four examples, and then hopefully we'll have a better understanding. So let's start with equation number one, example number one. And I'm gonna start with the famous Pythagorean theorem equation, which is a squared plus b squared equals c squared. And just to give a bit of context, this is the equation for a triangle with sides a and b and a hypotenuse c. So let's say that they ask us solve for b, and so we must isolate for b. Well, we have to start by subtracting a squared from both sides of the equation, or to isolate for b, and then we simply take the square root of both sides and we get what b is equal to, which is c squared, the square root of c squared minus a squared. So that's a very simple question. Now we'll move to another one, which is really cool. It's the combination of the gas laws, where P is the pressure, V is the volume, N is the number of moles, T is the temperature, and so now we're being asked to, let's say, solve for N2. Okay, well, let's first start by multiplying both sides by N2T2 in order to make it part of the numerator, which makes it easier to isolate. So N2T2 times P1 V1 over N1 T1 equals P2 V2. And then from here, all we have to do is divide by everything on the left side that is in N2. And so in that manner, N2 is equal to P2 V2 over T2 P1 V1 over N1 T1. And hence this is our result. Now, another example. Let's look at physics now, and there's this law when we're trying to find total resistance R, and we have, let's say, three resistors that are parallel to each other in a parallel circuit, and that would have to sum in the way that it's 1 over R1 plus 1 over R2 plus 1 over resistor 3, right? And so let's say now that they want us to isolate for what is R. Well, just for practice sake, we'll find a common denominator on the right-hand side of this equation so that it's more cleaner as an answer instead of having a lot of fractions that are inverses. And so we will simply leave the left side alone. And let's look at the right-hand side. Well, we're going to start by doing this, and I'll explain it a bit why this works. So just to look at this first, R2, R3 over R2, R3 is just 1. So we're not changing the equation out of nowhere. What we're trying to do is multiply this numerator by the other two variables involved in this expression with the hopes of doing the same thing for the other fractions and getting a common denominator. So then this is plus 1 over R2 times, you guessed it, R1, R3 over R1, R3. And I just noticed that I am writing over the image. So I'm gonna redo this a little bit so this is more obvious. So I'm just gonna continue here and think about this being one big addition on this right hand side. So then this is plus 1 over R2 times R1, R3 over R1, R3. Okay, then we're going to add 1 over R3, our last term in that right-hand side of the equation, and multiply it times R1, R2 over R1, R2. And so what this reduces to is 1 over R. We're gonna add all the numerators because we have the same denominator. And so this becomes R2, R3 plus R1, R3 plus R1, R2 divided by R1, R2, R3. And then all we do to isolate for R, well, it's already isolated, but to make it clean and it just be R, we're going to take the inverse. And all this is going to do is switch our numerator and denominators. And R over 1 is just R, so we'll just write R. Again, because we're taking the inverse. And this just becomes R equals R1, R2, R3 over R2, R3 plus R1, R3 plus R1, R2. And this is our answer. So I think this is good. We can do another example where we're gonna talk about the total energy involved in a simple harmonic system, which is the sum of the kinetic energy, half mv squared, plus the potential energy dealing with the spring. So K, the spring constant, x squared, distance squared. So now let's say they tell us find that distance that it has traveled due to the internal energy. And I'm just throwing all these physics terms around because I want to emphasize that physics is probably the most direct application of mathematics, at least at an intuitive sense. So that's why I'm talking a lot about physics examples. But let's just do this. And so in order to isolate for x, first we want to get rid of the half mv squared term. So we're going to subtract it from both sides in order to make it end up on the left hand side of this equation. And so we end up with this expression. And now what we do is multiply times 2 to get rid of the denominator on the right hand side. And we end up with 2e minus mv squared equals, because all we did was distribute it, the 2 to both terms in this left hand side of the equation. And now this right hand side is just kx squared. And we want to solve for x, so we'll have to divide both sides by k. And so divide that by k, divide this by k. This is canceling out. So then x squared equals 2 times the total energy minus mass times velocity squared over k. And now, last but not least, all we have to do is take the square root of both sides in order to isolate for x. And so x ends up being equal to the square root of 2e minus mv squared over k. And hence this would be our final answer. I think I'll stop it right there. These are pretty simple literal equation practice examples that I really wanted to go over, and I hope this helps.